So first of all, I would like to thank the organizers, Kavita, Tridib, and Sakuntala for organizing such a nice meeting. In some sense, it feels like homecoming to me. And everybody has talked about it before. This is a huge gratitude that I also feel towards Deepak and also Mustansir for the guidance that I got during my PhD. And in fact, that guidance has continued. I still feel that whenever I have a SOS, I have a confusion, I write to them and I get prompt, precise replies. So thank you very much for helping me, for shaping me, my view of the subject over the years. Okay, so the work that I'm going to talk today, it also has a very happy happy instance that finally I could actually work with Mustansir, and a large part of my talk will be based on the work which we did recently. And in fact, there are two papers which came out from this work, and both the papers got published in this month, in February 2022. And I'll be talking of systems with random fields and random crystals, which have been studied for a long time. And I'll be talking of two different kinds of spin systems, discrete spins, where the work has been done in collaboration with my graduate student Soheli Mukherjee, who was chairing the morning session and who is also in the audience. And then I'll be talking about continuous spin systems, where the work was done in collaboration with Mustansir. So the problem actually has a very long history, and it has been studied for last I don't know, 50 years or something. So since this is a short talk, I would perhaps straight go to the model definition and to new results that we have, but I'll be happy to take any questions about the connections with the previous work. So the kind of models that I am going to talk about can be defined through a Hamiltonian, like the one you see here, with a ferromagnetic coupling, and the disorder can be in the field. When then it couples directly to the spin through a term like hi dot si. The disorder can be in the crystal field, and then it couples through a term like di dot si dot square. And the spins, as I said, can be discrete or they can be continuous, and the nature of degree of freedom can change the behavior of the system a lot. I again the disorder in the field or the crystal field breaks the translational symmetry of the system, and we take this disorder to be frozen or quenched, just like we have quenched. So in that sense, the diffusion time of the disorder degree of freedom is very large, and we can still define a free energy, which is the expectation value of the partition function for a given realization of the disorder over the whole disorder distribution. We had two talks yesterday by Kedar and Professor Peter Krasberger, where they talked also of the quench disorder, which was the impurity disorder in the case of percolation. Here, disorder is in the force, the field that they feel, actual field that they feel at the site. So that is a slight difference in the quench disorder that I'm going to talk right now. Of course, the model has been studied, and one of the most popular methods which have been used to do this so-called disorder averaging, which is that which is the evaluating the value of the log z, is through replicas, which has been quite successful, especially on the random graphs. Though we still know, still there are a lot of questions when it comes to finite dimensions, because simulations in finite dimensions are still very hard due to the self-averaging. And that's becomes especially true when we have continuous spin systems. So I'll be talking of two systems. One is the spin one system, which is the Bloom-Kipple model, and the XY system, where the spin S is a XY spin. So let me first talk about the Bloom-Kipple model and the results that we get for the disorder averaging in this case. So before I go to the disorder model, let me just quickly remind you about the phase diagram of the pure model. So if I consider the pure spin one model with this Hamiltonian where hi is h and delta I is delta at all sides, in that case, the phase diagram of the pure Bloom-Kepple model in the T delta plane, if I make capital H to be 0, has a line of second order, which ends at a tricritical point TCP. And beyond that, there is a first order transition between the magnetized state and the non-magnetized state. If you switch on the external field, one finds this tricritical point, that is how it got its name, is a point where there are two other critical lines which meet, the lambda line, and these two lines which come from the finite magnetization, external magnetization state. So in the in the space of the three couplings, external field, crystal field, and the temperature, the phase diagram of the pure Bloom-Kepple model in dimensions 2 or greater looks something like this. We are going to look at the effect of the crystal field when we introduce a random crystal field for this model. And the random crystal field we have taken is drawn from our distribution P delta I, which is a bimodal distribution. That is, randomly at P sites, on an average, there is a field which is pointing in one direction, and for rest of the 1 minus P sites, it is pointing in the different direction. We solve it not using replicas, but we use, we define the probability that give a configuration with the typical values of the two order parameters x1 and x2, which are basically the magnetization and the density of the spins, satisfies the large deviation principle, and hence there is a rate function which can be associated with the probability distribution. And this rate function is actually like a generalized free energy, something that Tridib also talked about yesterday in the context of non-equilibrium systems. And the way we try to we solve the system is by finding this rate function for the given problem. I will just this is the only slide where I tell the idea of the calculation, and I'll just go very quickly. If we are dealing with the model for infinite range model, which is like defined on a fully connected graph, the problem can be solved quite easily. And the way to do it is, first we find the rate function corresponding to the non-interacting part of the Hamiltonian, and then we use the tilted large deviation to find the rate function for the whole problem. Okay, so we do all that procedure, and in the end, for the Bloom-Kepple random crystal field model, this is the rate function that we get. Okay, so now if we try to analyze this rate function, well, what do we find? Is the phase diagram same as the pure model, or does it change? So we find that the P, which defines the strength of the disorder, is always relevant, and it actually changes the phase diagram the moment we switch on the P. So there is, we can define a regime of weak disorder where we find that for weak disorder, the phase diagram still has this line of continuous transition, which ends at a tricritical point. But now there is a new critical line which shows up at very low temperatures. So there is a first order line. The first order line now does not go to 0 temperature. Instead, it ends at a point which is a critical endpoint. And beyond that, there is again a critical line. Okay, so this is how the phase diagram looks for weak disorder. If we increase the strength of the disorder strength, the phase diagram shows more interesting behavior. And what we find is that there's no tricritical point in the model beyond that strength of the model, strength of disorder, but the first order line stays for some more time. And now this first order line is bound by two critical endpoints and not a tricritical point. Tricritical endpoint is also a multi-critical point, is a multi-critical point where a second order line and a first order line meet. But the difference is that here, the second order line abruptly terminates, whereas in the tricritical point, the second order line actually ends there. Okay, and not just that, if that is the case, then if this happens to the tricritical point, the obvious question is what happens to the wings, the two critical lines which come when we switch on the external field. And we find that those two lines stay, but now they meet inside the ordered phase at h equals 0 at the star, black star that you see. And this point is now actually a bicritical point, because here instead of 3 lines, there are 2 lines which are meeting. Now, if we increase the disorder further, the first order.
2 more minutes.
Oh, okay. First order transition moves. So I think, this is more or less the Bloom-Kibble, and I was actually in the very start of my talk. So I will move on to the next model, which is the random crystal XY model, which I studied with Mustansir. Here the spins are the XY spins, and the crystal field is disordered. Okay. Here if I take the pure system, the phase diagram has a spin clock transition in the DT phase diagram from a transverse icing to a longitudinal icing. And the model was solved when we take infinite D strength, because it becomes a random bond icing model. We actually solve the model for finite dimensions, and the rate function looks something like this, where all these i's that you see are the modified Bessel functions of the kth kind. And from this, we find that the beta, the transition temperature, actually is independent of the strength of the D, and also to the nature of transitions, as long as the transition satisfies this condition, P alpha being P pi by 2 plus alpha, and it is always 2. The beta C is 2, which is the transition temperature of the pure crystal field model. Now, besides that, we see many other interesting features. For example, if now we take a biased bimodal distribution of the crystal field, just like in the Bloom-Kibble case, we find that in this case, there's a tetracritical point. Instead of a spin flop line, now there is a mixed phase at low temperatures. And this mixed phase is different for infinite D, where it is a mixture of just 2 different icing spins, to the case when the D is finite, and there the low temperature phase actually becomes a canted state, which we can, for large D, can calculate exactly the angle of the canting angle that this state makes with the x and y axis. We also solved the XY model for the case where we had disorder in the external field. And in this case, again, we can find the rate function. I'll quickly just show you the result. And the phase diagram is very similar to what one sees in the random field icing model. There's a line of continuous transition which ends in a tricritical point, and then there is a first order transition in the presence of disorder. But again, we find that the line of continuous transition is same for a large class of disorder distributions, and the ordered state has the symmetry of the distribution. This calculation actually, has one more use, because there were some other calculations in the literature of the same system, one by the group by Lupo Parisi and Ricky Tesargini, and the other by group using effective field theory. And they had found that the phase diagram actually had only a line of continuous transition without a tricritical point and re-entrance. So we find that the phase diagram is actually consistent with the old work of Arani and Schneider and Piet, and actually there is a tricritical line and a line of first order transition. With that, I just show you this summary slide. We have been using large deviation principle to calculate the free energy of infinite range random field spin systems. And for the models that I presented today, we find the phase diagram in the space of 3 fields for the Bloom-Kibble model, and we found the nature of the low temperature phases for the XY model, which are non-trivial when we have disorder. And also we found that there's a large range of distributions for which the nature of the phase diagram and actually the point of critical transition remains the same.
Thank you, Dr. Sumedha. The floor is open for questions. Mustansir Barma, do you have a question?
No, I don't have a question.
Okay. I see your hand raised. That's why.
Oh, I'm sorry.
So, Sumedha, these calculations were all done on random graphs, or?
They are done on the fully connected graphs.
Okay, but anything that you can say about usual Euclidean lattices? Or?
Okay, so I did not talk about Euclidean, so it's very hard. First of all, there is a upper critical dimension which is still debated, above which there is the order can be present in any of these systems, which by Emery-Ma arguments for discrete systems is believed to be 2, and for continuous spin systems is 4, and that is for the random field systems. One can have similar arguments for the random crystal field models, but they would give similar low critical dimensions for these models. But still, I think in 3 dimensions, there's still no consensus.
Okay, thank you. Yeah.
There's one more question from Prasad. Can one illustrate ensemble inequivalence in these systems?
Okay. So that is a very good question. Actually, we have looked at ensemble inequivalence. Spin ones, higher spin discrete systems show ensemble inequivalence for large range systems with large range interactions. And that is true for the Bloom-Kipple model. We also showed it for the repulsive Bloom-Kipple, Bloom-Emery-Griffiths model. But so the problem is that we don't know, except for the random energy model, how to solve the model in the microcanonical ensemble. That is something that we are interested in.
Okay. Thank you, Professor Sumedha, for a very nice talk.